Lesson 2, Set Theory, Sets and Set Notation. In mathematics, a set can be defined as a collection of distinct objects. For example, the numbers on the face of a die form a set. Those would be the numbers 1, 2, 3, 4, 5, and 6. Sets are usually denoted by capital letters or by a description inside curly brackets. An object in a set is referred to as an element. For example, the number 5 is an element of the set of numbers of a die. There are three general ways of defining the contents of a set. First, by listing the elements. For example, the set A equals, and then in curly brackets listing the elements 1, 2, 3, 4, 5, and 6. Maybe a description of the set in words. So the set A equals, and then in curly brackets, the natural numbers less than 7. We could also use set builder notation to describe the set. So for example, the set A equals, and we would say this as all x such that x is less than 7 and x is a member of the natural numbers. Recall, the curly brackets together is read as the set of. The straight line up and down represents and is read as such that, and that funny looking E symbol represents and is read as is a member of or is an element of. The number of elements in set A is written as n, then round brackets A. In the above example, n, or the number, in the set A is equal to 6. Just want to add a note that if the number 2 belongs to set A, but the number 8 does not belong to set A, we could express this by writing 2 is a member of A, that's that funny little E symbol, and we could also use 8 is not a member of A, and that is that E symbol with a slash through it. Also, the order of the listing of elements does not matter, so the set of 1 and 2 would be the same as the set of 2 and 1. Let's take a look at example 1. Consider the following sets. Set P is equal to the set of natural numbers less than or equal to 3, and set Q is the set of even natural numbers less than 10. So for part A, we're going to list the elements of each set. The set of P is going to be natural numbers, so that does not include 0, it starts at 1, and we want less than or equal to 3. So that would be the elements 1, 2, and 3. Q would be the even numbers, less than 10. So that would start with 2, 4, 6, 8. It would not include 10 because 10 is not actually less than 10. It is equal to 10. Complete the following. So the number of members of set P, that would be 3. The 1, the 2, and the 3. The number of elements in set Q is equal to 4. Part C. Write set P using set builder notation. So the set P is equal to the elements x, so we're going to list various values for x such that x is less than or equal to 3, and x is a member of the natural numbers, so that would be 1, 2, and 3. For part D, this is very tricky. Which of the following is the set builder notation that describes set Q? Let's just take a look at A for a second. It says that the set Q is equal to the values of x such that x is less than 10 and that x is a member of the natural numbers. That would include 1, 2, 3, 4, 5. That's too many. It's not going to be the correct possibility for this, for set Q. Now, B, C, and D are quite a bit more complicated. We've got a few more restrictions here on what our elements can be. And if you notice now, we have two variables that we are using to describe this. So Q is what it's saying for part B is that Q consists of the elements E, such that E is equal to 2x, and that x has a value of 1 to 10, and x is a natural number. So if we started with 1 and placed it in for x, we could have e equals 2 times 1, which is 2. 2 is an element of set Q. Let's try 2. 2 times 2 is equal to 4, and 4 indeed is an element of set Q. But what if we tried x 7? 7 fits between 1 and 10, and that's a natural number. And e would equal 2 times 7, which is 14. But is 14 included in that set? No, it's not. So that would not work. If we look at C, for C we're just using x values between 1 and 4. And if x was 1, 2x would be 2. If x was 2, it'd be 2x, which is 4. If x was 3, it would be 2 times 3, which would be 6. Terminology used in set theory. Brenda is defining sets using non-negative single-digit numbers. So that would be from the digits from 0 to 9. And from the list of non-negative single-digit numbers, she defined the following sets. E is the even numbers. L is the whole numbers less than 7. And O is the odd numbers less than 7. List the elements of each set in the space above, and we will use these sets as an aid to understanding some of the terms that we use in set theory. So for the set E, being the even numbers, 0 is considered even, 2, 4, 6, and 8. The whole numbers, less than 7, would be those numbers 0, 1, 2, 3, 4, 5, and 6. The odd numbers less than 7 would be 1, 3, and 5. Okay, our first definition is the universal set. Within the context of any problem in set theory, there generally is some largest set that we have in mind. We refer to this set as the universal set. It is the set that contains all the elements under consideration and relevant to the problem. So for the example above, the universal set will be all the non-negative single-digit numbers. This would be 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Subset. A subset of a set is a set that contains some, or all, or possibly none of the elements from a previously defined set. All sets we deal with in a problem must be subsets of the universal set, and every set is a subset of itself. In set notation, the symbol is a subset of, which looks like a sideways U, is used to represent this relationship between sets. For example, set E is a subset of set U, since all the elements in set E are also in set U. This is denoted by E is a subset of U. Set E is not a subset of set L, because 8 is a number of E, but not of L. This is denoted by E is not a subset of U. So that's that funny sideways U with a slash through it. Set O is a subset of set L, which is a subset of U. So we can string these along and can be denoted by 0 is a subset of L, which is a subset of U. Empty set. The empty set is a set that contains no elements. The empty set is a subset of every set. We recall, we have seen this before, we will use either the empty set symbol, which is a 0 with a slash through it, or 2 curly brackets to denote this. Complement of a set. The complement of a set A is the set of all elements in the universal set that are not in set A. The complement of a set A is denoted by A prime. For this example, the complement of E, which is the even numbers, would in fact be the odd numbers. So E prime equals the set of 1, 3, 5, 7, and 9. Venn diagram. We have seen these before, and what we have in this case is a universal set represented by the rectangle, and the three sets E, L, and O are represented by the circles. We can place the numbers 0 through 9 into the Venn diagram in the correct spots so that we can see the relationship between the sets. For example, 0 is an element of the evens and the numbers less than 7, so it would go in that space between that overlaps E and L. 1 is an odd number and it's a number less than 7, so it fits in the overlap between L and O. And we can continue on with this pattern. Notice that 7 and 9 are not in any of the sets E, L, or O, but are contained in the universal set, so they will be outside the circles, yet still inside the rectangle.